Greetings everybody and welcome back to another video. What are we doing today? We're taking a look at the 2021 Methods Exam 1. Don't think I've done a video on this yet, so might as well make one. I do remember taking a quick look through this exam last year. I don't think it was too bad of an exam though. The final question was probably a little bit tricky on some level, but yeah, I don't think it was too bad of an exam overall. So let's just jump straight into it and see how we go. So first of all, standard derivative question differentiates this exponential function. How do you differentiate e to the something? Well, it's just e to the something once again, but then you got to remember chain rule as well. You multiply by the derivative of the inside, which is -3. So overall, dy dx, that's just going to be equal to -6, because you multiply by the -3, e to the -3x, because derivative of e to the something is e to the something. Next up we got f prime of 4, where f prime is this function. So we got the product over here because we have x times some other function. So if you want, you can call this guy over here, you can call that u, and you call this guy v. What does product rule tell you to do? I remember it as vuv, so vu dash plus uv dash. Okay, so what is v? V is just, well, first of all, let's write down f prime of x. So v is precisely the square root of 2x plus 1. That's the v. What's the u dash? U dash is just 1, the derivative of x. And then we have plus u, which is x. And then v dash. Now, what is v dash? How do you differentiate a square root? This is something I tell people to memorize all the time. Just the derivative of the square root of x, because you don't want to use power rule all the time. This is just 1/2 square root of x. It's something nice you can just memorize, and it's not too tricky to memorize anyways. So the derivative of square roots of something is just 1/2 times the square root of that something. Okay, now we look at v over here. What is v prime going to be? Let's write it up over here. It's just going to be, well, we have square roots of something. So first of all, it's going to be 1/2 square roots of something. So the something is the 2x plus 1. But remember, because there's something on the inside, you've got to use chain rule. What's the derivative of the inside? It's just going to be 2. So we multiply by 2 here. So that first part, that's the derivative of the square roots of something. And then that second part, that's just the inside derivative. So you chain rule it together, I guess. So I guess the 2 cancels, and what are we left with? We're left with 1 over the square root of 2x plus 1, like so. Okay, and we can just plug in 4 and see what happens. So f prime of 4 is going to be equal to, we have square roots of, well, 2 times 4 is 8, plus 1 is 9. Then we have plus 4, and then 1 over, if you plug 4 into that square roots part there, that's going to give you square root of 9. Okay, and that's going to be 3 plus 4 divided by 3, which is 9/3 plus 4/3, which is 13/3. Hopefully that is correct. Question 2, we got cubic, we got a derivative equal to a cubic, and we want to find the function f. So to go from derivative back to function, we got to integrate. So let's try to integrate x cubed plus x. So f of x, that's going to be equal to the integral of x cubed plus x dx. Okay, but that's just reverse power rule. So you raise the power by 1 and you divide by the new power, and then we have plus 1/2 x squared, because that's x raised to the first power. And then we also got to remember the plus c. Now we kind of want to find what c is, and to find c, we're going to use this condition over here. So when we plug 1 into the function, we expect to get out 2. So I usually write it this way. 2 is equal to f of 1, and you just plug 1 into the function you have so far on the right hand side. That's going to be 1/4, and then plus 1/2, and then plus c. And then you're just going to solve the equation. I mean, we can simplify this a little bit. This is 3/4 plus c. So let's see, c is equal to 2 minus 3/4, but that's just going to be 8/4 minus 3/4, and that's going to be 5/4. So therefore, the function f of x is just going to be 1/4 x to the 4 plus 1/2 x squared, and then plus 5/4. Here we go. Alright, question 3. how many marks was that? That was 5 marks, and we're at 5 minutes. So it looks like we're ahead of schedule slightly. Question 3. We are taking a look at 2 sine of 2x. State the range of g. Nice and simple. The mean position is 0 because there's no vertical translation. So you just take the standard range of the sine, which is -1 to 1, multiply it by the amplitude, so it becomes -2 to 2. State the period of g. Nice and simple once again. You just take 2 pi divided by the coefficient of x on the inside there. So what's 2 pi divided by 2? It's just pi. So I think those would be 2 marks altogether. And then for 3 marks, we're supposed to solve this for x in the real numbers. So if there's no particular domain restriction, then this is general solutions. So let's see how we can do this over here. First of all, to solve a trig equation, we would like a sine of something equals something. Now there's that 2 on the left hand side, so let's move it over. So we have the sine of 2x is equal to root 3 over 2. Okay, and now, well, let's just try to figure out some values for 2x. So we're going to pretend we solve for 2x. So what does sine look like? Sine is the y value. So if you imagine the unit circle over here, we're asking ourselves the question, what angles on the unit circle have a y value of root 3 on 2? So if you imagine the line square root of 3 over 2, well, that's going to be pretty high up. It's pretty close to 1. So you're taking a look at the y values all the way up over here, like right near the top. So these 2 angles over here, what's the 2 possible values for those 2 angles? Well, it's going to be pi on 3 and 2 pi on 3. So make sure you know your unit circle well. Comes in very handy to be able to do, or to be able to find angles very fast in exams. Okay, so we have those 2 angles. So therefore, what we can say is if 2x is equal to pi on 3, then it satisfies this equation. But the thing is, we could have pi on 3, or we could spin around another time. We'd still get back to the exact same position. So all you have to do is just add 2 pi times some constant k, where k is an integer to be precise. And then remember, we also got this other solution on the left hand side over here. It's the 2 pi on 3. So 2x could also be equal to 2 pi on 3. But once again, we could spin around another time, or we could spin around backwards and so on. We just need to add an extra 2 pi and a k, and it satisfies as a solution that sine of 2x is root 3 on 2. Okay, but we wanted to find x in the very beginning, and by the way, I should also mention that k is an integer. So we want to find x, so just divide by 2. So our final answer should look something like this. X is equal to pi on 6 plus pi times k, or x is equal to, we have pi on 3 and then plus pi times k, where k is an integer. Right, so for the function sine and cosine, we usually add the 2 pi k here, because if you have a particular point, you can always do full revolutions around or backwards whatsoever to get back to the same point. But for tangents, it's enough just to add pi times k here. Right, because if you identify one possible solution for the tangent, then the other solution, first of all, will always be on a half circle away. And you can keep just basically adding half a circle every single time, pretty much. Hopefully that makes sense. If not, you can ask in the comments, or I don't know. Yeah, hopefully that made sense. So that's the answer for 3 marks. Question 4. Sketch the graph of y equals 1 minus 2, x minus 2 on the axes below. There's no domain, which is good, so we can just graph it across the whole real line. So label asymptotes with their equations, and okay, intercepts and so on. So first of all, what are the asymptotes? That's probably the most important thing you should get. Asymptotes x equals 2, because that's what makes the denominator 0. So we can put a nice line down here, and you should, let's use a ruler. You should really use a ruler for this. So let's use a ruler. So we've got x equals 2. And how about the y asymptote? Well, it's just going to be y equals 1, because that's the extra constant. That's not involved in that fraction. So where's y equals 1? Probably over here. So we got something like this going on. Okay. Now what's the orientation of this hyperbola? Is it's top right, bottom left of the asymptotes, or the other way around? Well, the way you tell is take a look at the negative over here. There's a negative, so there's a reflection going on. So usually our hyperbolas look like this, but now because it's reflected, it's going to look like this. Okay, so we know it's going to have this type of shape, and before you graph any of that stuff in, you should probably figure out the x-intercepts, just so you have a guide of where to put things. So let's do x and y-intercepts. Let's do the y-intercepts first because it's easier. So what are the y-intercepts? If you plug in x equals 0, you're going to get y equals 1, and then minus 2 over negative 2. But that's just going to be 1 plus 1, which is 2. So the y-intercept is at 2, right over here. Let's label it before we forget, and we should probably label the asymptotes as well. So y equals 1, x equals 2. So this is the point 0, 2. How about the x-intercepts? So the x-intercepts we get by solving y equals 0. So we have 0 is equal to 1 minus 2 over x minus 2. Let's bring that fraction over. So we have 2 over x minus 2 is equal to 1. Let's multiply by x minus 2. So we have 2 equals x minus 2. And let's solve, nice and simple. It's just going to be x is equal to 4. So let's put that in right over here. So all this was just working out. So let's put that in a little nice bubble like so. So x equals 4. So that's once again label before we forget. So 4, 0. And then now we just need to put lines everywhere. So maybe something like this will do, hopefully. Actually turns out quite nice. Usually I'm not that great at drawing graphs on my little tablet thing here. And that should be it. So we sketched the graph on the axes, label asymptotes. We've done that with their equations. Yes, we have. And axis intercepts. We've done that as well with their coordinates. Perfect. To find the values for which this guy over here, our function, is greater than or equal to 3. So in particular, well, this is the function we graphed, y equals this function. So we're essentially asking, where are the y values greater than or equal to 3? So where is 3? Well, y equals 3 is over here. So we're trying to figure out which values of x makes this graph greater than or equal to 3. So as you can see, hopefully we're looking at this range of values over here. So let's see if we can get that. So first of all, how can we do this? We can try solving the inequality, I guess. So let's bring that fraction over, and then we'll subtract 3 from both sides. So we have negative 2 is less than or equal to 2 over x minus 2. So notice we're not flipping the inequality sign because we're not multiplying by negatives or anything. We're just swapping the order of things. Okay. Now what can we do? We can multiply both sides by x minus 2. Now here's where we have to be careful, because we don't know if x minus 2 is negative or positive. Right? Now if we take a look at this picture, we can see that we're only interested on the left-hand side of the asymptote x equals 2. So we're not interested in the right-hand side at all, only the left-hand side, because that's when we're going to be greater than 3. So because we're only interested in values on the left-hand side of x equals 2, what is x minus 2 positive or negative? Well, the values of x are less than 2, so if you subtract 2 from it, then x minus 2 is negative. So hopefully that's clear there. So since we want x to be less than 2, we're only interested in this region, x minus 2 is negative. So when we bring that denominator over, we better flip the inequality sign. So 2x minus 2 is less than or equal to 2. Okay, and now we can distribute on the left-hand side. So we have negative 2x plus 4 less than or equal to 2. And then we can just solve things as usual. So 2x is less than or equal to negative 2, I think. So x is, let's say we divide by negative 2, so that's going to flip the inequality sign. So this is greater than or equal to 1. Right, so x is greater than or equal to 1, but remember, we want x less than 2. So what's the intersection of those? it's 1 less than or equal to x less than 2. That should be the answer. And if you take a look at the picture, if you have a graph, it's always nice to visualize what's happening on the graph just to make sure your answer makes proper sense here. If you take a look at y equals 3, you can see if you draw your graph accurately enough, it doesn't have to be perfect, but as you can see, between 1 and 2 over here, in this range, our graph is always above 3, so that makes sense there. So I'm fairly confident that should be the right answer. Okay, question that was 4, so let's take a look at 5. So what do we have here? We have a function, it's x squared minus 4, and g is another sort of quadratic. The graphs of f and g have a common horizontal axis intercept at 2, 2. Find the coordinates of the other horizontal axis intercept of the graph of g. Okay. So I guess we're just going to solve g is equal to 0 because we're trying to find horizontal axis intercepts or x-intercepts. So I guess let g be equal to 0. Then what does that mean? It means that 4x minus 1 but squared minus 4 is equal to 0. Okay, but what does that mean? You can divide both sides by 4 and you're going to get x minus 1 squared. This is equal to 1 because you cancel the 4 over here, so that gives you a 1, and you move the negative 1 over. And what we can do is we can square root both sides, so x minus 1 is equal to plus or minus 1. So therefore, if you add 1 to both sides, we have x is equal to 1 plus 1, which is 2, or x equals 1 minus 1, which is 0. So they have a common horizontal axis intercept at 2, 0. Okay, that's one of them. And the other one, that should be 0, 0. So I think we've gotten that one. So you can test it. If you plug 0 into here, you're going to get, negative 1 squared, which is 1, and 4 minus 4 is 0. Perfect. Okay, now let the graph of h, did we have a h here? We didn't have a h. Be a transformation of the graph of f. So here's the graph of f, it's x squared minus 4, where the transformations have been applied in the following order. So we have a dilation, then we have a translation to the right, then state the rule of h, and the coordinates of the horizontal axis intercepts of the graph of h. Okay, so first of all, what happens, so we're transforming the graph of f here, so that's the x squared minus 4. So let's start with x squared minus 4. What happens if we dilate by a factor of a half from the vertical axis? Well, if you dilate by a factor of a half, what you're going to do is you're going to replace x with 2x. Remember, when you dilate from the vertical axis in the functions, you always have to take the reciprocal of that dilation, only if it's from the vertical axis. So we're going to replace all the x's we see with exactly 2x. So this becomes 2x squared then minus 4. And then we translate 2 units to the right. So what happens if you translate 2 units to the right in your functions? Well, you're going to replace all the x's with x minus 2, because that's 2 units to the right. So this guy, that's going to become, what I should really do is instead of 2x over here, let's do that. Let's make that red. So this is the 2x. That's too big. So this is the 2x here. And on the next step, we're going to replace x with x minus 2. So this is going to become that 2's there. And then we're going to replace the x with exactly x minus 2. And this is squared, then we have minus 4. That should be right, hopefully. So dilate by a factor of a half, then translate 2 units to the right. Okay. And then what do we have to do? Well, this is the graph, I guess. So let h, state the rule of h. So I guess we could state it in this fashion, but maybe let's expand things out a little bit. Maybe that's a bit nicer. So h of x. Did we have a domain up over there? We didn't. It's just r, which is technically a domain anyways. But so h of x is equal to, well, it says state the rule of h. I always forget if it includes the domain or not. Maybe we'll just include the domain just to be safe. So r to r, and then h of x, that's going to be equal to, we have 4 and x minus 2 squared minus 4. Isn't that the function we literally just solved. No, it's pretty close to G though. Now what's the difference between H and G? H and G only differ by a translation along the x-axis, it looks like. Because how do you get from G to H? Well, you're just going to translate 1 unit to the right. Because what is a translation 1 unit to right? Well, in the functions, you're just replacing x with x minus 1. If you take G and you replace x with x minus 1, you're going to get to H. Okay, so that's nice. Now, because we know the x-intercepts of the graph of G, it's 2, 0, and 0, 0. And we know how to get to H from G. We just shift things to the right. We're just going to add 1 to each of those x coordinates. Right, so let's be clear about this. It's to get from G to H over here, this is a translation by 1 unit right. Okay, so the x-intercepts of G was 0, 0, and 2, 0. So the x-intercepts of H, they're going to be 1, 0, and 3, 0. Because you're just translating thing 1 unit to the right. Okay, that's question 5. That's the halfway point, I think. Looking pretty good on time. We're at 21-ish minutes. Question 6, an online shopping site sells boxes of donuts. I remember this question. It was the glazed donuts and whatnot with custard. So we have 20 donuts. There are 4 types of donuts in the box. So here are the 4 types. Now it's known that half of the donuts are with custard, 7/10 of the donuts are not glazed, and 1/10 of the donuts are glazed. So you can kind of see 2 categories here. Okay, glazed or not glazed, then with custard or no custard. So if you have 2 categories and there's a bunch of combinations, it's probably a good idea to draw a Venn diagram to represent all the probabilities. So let's do that. Let's do a little Venn diagram. So we'll do glazed over here and custard. So let's do G for glazed and C for custard right over here. So what do we know? We know 1/2 of the donuts are custard. So this circle, let's actually do a bit of color coding. So let's do glazed in green, and let's do custard in yellow. So this custard circle, that has to be a probability of 1/2. 7/10 of the donuts are not glazed, which means the glazed donuts, there should be 3/10 of the donuts which are glazed. So this green circle should be 3/10. Now 1/10 of the donuts are glazed with custard. Okay, so 1/10 goes in this intersection here. So this intersection is 1/10. Now because we know the green circle is 3/10, we can figure out just the green circle without the custard. So glazed without custard, that's 3/10 minus 1/10, which is 2/10, which is 1/5. How about the custard side? Well, what's the probability of getting a donut with only custard and not glazed? Well, you just take 1/2 and you subtract off 1/10. Okay, but 1/2 is 5/10. If you subtract off 1/10, that's 4/10, but 4/10 is exactly 2/5. And we can figure out the remaining, the outside. We'll just leave that because I'm too lazy and it might not be required. So let's find the probability that it's not glazed with custard. So not glazed with custard is just the 2/5 on the right hand side here. So that's 2/5. Question B, the 20 donuts in the box are randomly allocated to 2 new boxes, A and B. Each box contains 10 donuts. Okay. One of the 2 new boxes is chosen at random, then a donut from that box is chosen at random. Let G be the number of donuts in box A. Find the probability in terms of G that the donuts comes from box B, given that it's glazed. What on earth is that saying? Okay, let's think about this carefully. So 20 donuts in the box. So this is one big box of donuts. And inside of that big box is 4 types of donuts. Okay, we understand that. And there's this distribution of different types of donuts. So we're going to have 2 new boxes, A and B. So here's box A. And here's box B. Now, what on earth are we doing with this? So each box contains 10 donuts. So we don't know what type of donut goes in there. We know there's 10 in each. One of the two new boxes is chosen at random. Then a donut from that box is chosen at random. Let G be the number of glazed donuts in A. Okay, so in box A, there's 10 donuts in total. So within that 10, there's G glazed. That's not how you spell glazed, it's a Z. So there's G, that's a glazed. And also, inside of this box A, well, there should be 10 minus G that's not glazed. Okay. Now, how about in box B? Well, how many glazed donuts are there in total? Now I'm getting very confused. So there's G in box A. Find the probability in terms of G that the donut comes from box B, given that it is glazed. I'm very rusty on this. So find the probability in terms of G that the donut comes from box B. So the probability that we have box B, given that it is glazed. Okay, so let's do this conditional probability. So this is the probability that it's box B and it's glazed, divided by the probability that it's glazed. So what's the probability that it's glazed? Well, it is exactly 3/10 over there. Okay, so this is 3/10. Now what's the probability it's box B and it's glazed? I think for that we need the total number that are glazed. So 3/10 of the donuts are glazed. There's 20 donuts in total. That means there are 6 glazed donuts. Let's note that down. So over here, there's 6 glazed donuts in total. I keep writing S there. So this is 6 glazed in total. So, okay, I guess this 10 minus G not being glazed isn't very useful information. Maybe it is, I don't know. But because there's G glazed donuts in A, only G glazed donuts in A, now there's 6 glazed donuts in total, that means the other 6 minus G must go in B. So inside of B, 6 minus G glazed. That makes sense. So now we ask ourselves the question, the probability of B and glazed. Okay. So you can think of a tree diagram maybe, because if this is multi-stage, because first of all, you either pick box A or box B. So I should really put them over here. So it's either box A or it's box B. And this is 1.5 probability each, because this is selected at random. And then inside of box A, you have glazed or not glazed, and in box B, you have glazed or not glazed. I think a tree diagram would have been helpful if I've thought of that earlier. So in box A, the probability of glazed is G on 10. And in box B, the probability of glazed is exactly 6 minus G on 10. Okay. So the probability of glaze is 3/10. Now we want a B intersects G. That's going to be a half times, well, this guy over here. 6 minus G on 10. So it's a half times 6 minus G on 10. Okay, what is that going to be? Let's multiply the top and the bottom by 20, just to cancel out with that 2 and the 10. So that's going to give us 6 minus G divided by, what's 20 times 3/10? Well, that's going to be 6. And I'm quite sure that's the final answer. So 6 minus G on 6. I don't know how you would think of that question though. Very confusing question. Oh, we got part C as well. Oh dear. So online shopping site has over 1 million visitors per day. So 1 million was talking about a very big population over here. It is known that half of these visitors are less than 25 years old. Let P hat be the random variable representing the proportion of visitors who are less than 25 years old in a random sample of 5 visitors. Okay, so we have 5 visitors, random sample of 5 visitors. So this is small sample, right? N is equal to 5. So if we have a small sample and we have a large population, we use the binomial approximation for P hat. So what we're going to do, use binomial approximation Now, how does the binomial approximation work? What we're going to do is just set up a new random variable at x, so let x be binomial, with a sample size of 5, and what's the probability of success? Well, it's just the population proportion. So it is then that half of these visitors are less than 25 years old, and p hat's the proportion of people who are less than 25 years old. So a successful person has a probability of a half. So what we do to find the probability that p hat is greater than or equal to 0.8, we simply convert it over to the x distribution, so the binomial distribution. And you do that just by multiplying everything by the sample size. So in here, you multiply by an n, and 0.8 you multiply by an n. So n times p hat, that's just going to become x because of this relationship. P hat is equal to x divided by n. So x is greater than or equal to n times 0.8. What is n? N is 5. So 5 times 0.8 is exactly 4. So probability that x is greater than or equal to 4 is what we have to calculate. Yeah, that's not too bad to do, because to calculate the probability of the inequality, you just split it up. So x equals 4, and then plus probability x equals 5, and you can't go higher than that because you can only have 5 visitors. You can't have more than 5 successful visitors. So you just use the binomial formula for this. So this is 5, choose the x value, then the probability of success, so this is 1/2, raised to the number of successes, which is 4. Then you do a half, raised to the number of failures, which is 1. Then you do plus 5, choose 5, successes to number of successes, failures, or probability of failure to number of failures. So what's 5 choose 4? It's exactly 5. In general, if you have n choose n minus 1, it's just going to be n. And what's 5 choose 5? It's just going to be 1. And once again, in general, if you have n choose n, it's going to be 1. So let's write it down. Might as well give you guys the formulas over here. So if you have n choose 0, that's 1. If you have n choose 1, that's n. If you have n choose n minus 1, that's n. And if you have n choose n, that's just going to be 1. Right, so let's clean things up a little bit over here. So we have 5, then 1/2 raised to the 5th. Then we have plus 1/2 raised to the 5th. So overall, this is a 6 times 1/2 raised to the 5th. What is 2 raised to the 5th power? Well, I know 2 raised to the 4th power is 16. So 2 raised to the 5th power is 32. So this is a 6 over 32, which you can simplify as 3 on 16. We'll take that as our answer. Okay, how many marks was that? I think I spent like 10 minutes on that, maybe even more. That was 6 marks. I don't know how long I spent on that. Probably like 10 minutes. Not too bad though. We're just slightly behind. Actually, we're still ahead of schedule, I think, because of the other questions. Anyhow, question 7. We have a random variable. It's k over x squared. So this is probability density function. Show that k is equal to 2. How do you do that? Well, you just need to integrate your density and make sure it's equal to 1. So let's integrate from 1 to 2 of the density. So kx squared dx. How do you integrate, first of all, we have the k, but how do you integrate 1 over x squared? It's just negative 1 over x. So this is x, and we have a negative, and we might as well bring out that k as well. So negative k 1 over x, and we're going from 1 to 2. Okay, so this is equal to negative k. Let's plug numbers in everywhere. So we have 1/2, then minus 1. A half minus 1 is negative a half, so minus k times negative a half. That's just going to be 1/2 k. And we really want this to be equal to 1. So therefore k is equal to 2. Find the expectation. So how do you find the expectation of a continuous random variable? You integrate x times the density. So this is x times f of x, might as well write it like that. So this is just the integral from 1 to 2 of k, but k is equal to 2, so it's 2 divided by x. Because the x and the x squared will cancel to an x, dx. How do you integrate that? It's just a logarithm. So we have 2 on the outside, then we have a log e of x, and we go from 1 to 2. Then we just plug numbers in, so this is 2. Log of 2 and then minus log of 1. But log of 1 is precisely equal to 0. So therefore, I keep forgetting to put e's down here. So therefore, it's just going to be 2 log BC of 2. We'll take that as the answer. Is that all for question 7? Perfect. So we got question 8 now. The gradient of this function is, well, some square roots with some other stuff attached to it. The graph of the function has a single stationary point at 3, 29, and 4. Finds the rule of the function. Okay, so what are we working with over here? We want to find the rule of the function. We're given the gradient, and here's the stationary point. But in general, this is just the points that we know, which is good. Okay, so we just need to integrate this thing now, which isn't too bad to do. So y is the integral of square root of x plus 6, and then minus x on 2, and then minus 3 on 2 dx. So what is that going to be? How do you integrate a square root? Well, let's just do it on the side. Square root of x. If you integrate this is going to be turned into. Let's clean things up a little bit here. So this is the integral of x to the 1/2 dx, but that's just going to be equal to 2/3 times x to the 3/2 plus c, because 1/2 plus 1 is 3/2. So what is this going to give us? It's going to give us 2/3. We have the x plus 6, and then this is raised to the power of 3/2 and plus c, but we can leave that till later. And then we have negative. How do you integrate x? Well, it's just going to be x squared on 2, but because we have the half there, that's just going to give us 1/4 times x squared. Then we have minus 3 on 2 times x, and we have a plus c. Alright, so now we need to make sure that this function passes through the points 3, 29 on 4. So let's plug that in here. So the y value is 29 on 4, and we need to make sure that's what we get if we plug 3 in everywhere. So we have 2/3, we have 9 to the 3/2, minus 1/4, and we have 9 once again. And is that correct? Yes, that is correct. And then we have minus 3 on 2 times 3, then plus c. So let's see if we can simplify this. What's 9 raised to the 3/2? Well, 9 raised to 1/2 is 3. You take 3 cube it, that's 27. But then you divide by 3 yet again down here. So that brings it back to 9. That's 18 overall because you multiply by the 2. Then we have negative 9 divided by 4. Then we have negative another 9 divided by... No, this is 9 divided by 2 now. Okay. And then we have a plus c, so this is equal to 18. We have negative. Let's write that 9 on 2 as 18 on 4, so we can combine it. So 9 on 4, then minus 18 on 4, plus c. This is very long here. So this is 18 minus 27 on 4, then plus c. How much arithmetic do they want us to do here? So 18, or maybe I'm just overcomplicating this, I don't know. This is equal to 18, what's 18 times 4? 18 times 2 is 36, so that's going to be 72 on 4. Plus c. This is ridiculous. So 72 minus 27, or maybe there's an easy way to do this and I'm just not seeing it for some reason. What's 72 minus 27? I'm horrible at arithmetic here. So 72... How does this work again? You take, doesn't it work like this? Like you subtract 1, you bring it over, something like that. Haven't done this in years. And then 6 minus 2 is 4, probably. So 45. This is 45 divided by 4, plus c. So what do we want? We want 29 and 4 to be equal to 45 and 4, plus c. So let's just subtract 45 and 4 on both sides. And let's see what we get. So c is equal to 29 on 4 minus 45 on 4. And that is going to be equal to... I have to do it again. Maybe not. So that's just going to be negative 16 on 4, I think. That's negative 4. That is ridiculous there. Hopefully negative 4 is correct. So if that is the case, then let's do the therefore over here. So this is 2/3 x plus 6 raised to the 3 on 2 minus 1/4 times x squared minus 3/2 times x, then minus 4. I'm really hoping I got all the arithmetic right there. If not, I'm going to cry. Not that it matters anyways, but yeah. Anyways, part B, determine the nature of the stationary point. So how do you determine the nature of a stationary point? Well, you center yourself on the x value, so 3. Then you just take a look on either side and see what happens. So you do take a look at the derivative function in particular. So you do, I think it's the sine table or something like that, or the derivative table, I don't know what it's called, something like this. So take a look at your dy on dx over here. No, the dy on dx goes at the bottom. So dy on dx, and you take your x value, you center yourself at 3, and you just pick 2 values. And because there's only one stationary point, it doesn't really matter how far out you go. So let's just pick a nice value. For example, let's pick x equals -6 or something, because that's just going to kill off that square root. So got -6. That's going to kill the square root. If you plug -6 into negative the x on 2, that's just going to give you 12 on 2, which is 6. Is that right? No, it's not. If you plug -6 in, that's going to give you 3. Right, because that's -6 over -2. So that's 3. Then we have -3 on 2. So 3 minus 3 on 2 is definitely positive. So something like this. 3 is a stationary point. And what happens? What other number can we choose? Let's choose maybe, let's choose 3. So what happens at 3? Well, actually at 3 it's already 0, so there's no point checking that. Let's choose 10, because that's going to make this square root a nice number. So what happens if you plug 10 into there? You're going to get the square root of 16, which is 4. Okay, so 4, and then minus x on 2, so that's going to be, no, I have to write this out. So we have 4 minus, if you plug 10 into there, that's going to give you 10 over 2, which is 5. So automatically that's negative. So don't even have to check that negative there into. It's just going to be a negative gradient. So yeah, local maximum. You probably need to show a bit more working out than that, but I'm too lazy to do that, so I'll just leave it like that. Alright, it's question 9. Is that the final question already? I thought there were 10 questions. Oh well. So question 9. So we are at 43 minutes now. Not too bad. So we should have plenty of time to do this 8-mark question before we hit 1 hour. So question 9, consider the unit circle and the tangent at the points P. Show that the equation of the line that passes through A and P is given by this equation. Okay, so P, is that a tangent? Consider the unit circle and the tangent to the circle at the point P. So this is a tangent indeed. So how do we do this over here? First of all, let's try to figure out that point P there. That might be a good start. So how can we do that? First of all, we know it's on the unit circle. We just have to figure out maybe what angle it's at. That might help. We also know there's a right angle right over there. That's a right angle, so that's also going to help. This is a unit circle. So what do we know about a unit circle? So the radius is 1, so that's side length along the triangle there is 1. And we also know the hypotenuse of this triangle as well. It's going to be 2, because the x-intercept is at 2. So if we extract that triangle, that's not the right direction. Can I spin this around? Maybe something. No, that's not going to work. Oh well. So let's do something like this. Let's draw. Now it doesn't want to turn into a right angle triangle. Turn into a right angle triangle. There we go. So let's take this. Now I can rotate it. There we go, that's what it wants. So we have something like this. We know this side is 1, this is a right angle. This hypotenuse is exactly 2. So we should be able to figure out potentially this angle over here, because that's going to be the angle theta. So that's theta. So we're working with cosine over here. Cosine is equal to adjacent over hypotenuse, so a half. So what value of theta does the job? It's pi on 3. That point P is pi on 3. Alright. So what's the coordinates of P then? So the coordinates of P, that's just the x value and the y value of the angle pi on 3. So you can get that just by applying sine and cosine. So cosine for the x value, that's going to give you a half, and sine for the y value is going to give you root 3 on 2. That's the coordinates of the point P. So once we got that, it's not too tricky to show that this equation here holds. So first of all, let's figure out the gradients of this line. And well, the gradients, is there a shortcut to this? I'm not too sure. There might be though, because this angle is theta. So the gradient is just going to, the gradient of this line over here, of that line, is m is equal to tan of pi on 3, because tangents gives you the gradients. What's tan of pi on 3? This is going to be root 3. So the gradient of this line is this going to be the negative reciprocal, so minus 1 over root 3. So that gets this negative 1 on root 3 sorted. So far we have y is equal to negative 1 on root 3 times x plus c. Now we just have to figure out c. Let's plug in the simplest points we know, which is 2, 0, which is a point that the line lies on. So we have 0 is equal to negative 1 over root 3 times 2 plus c. So that tells us that c must be equal to 2 on root 3 if you bring it over. So therefore, y is equal to negative x on root 3, and then you have plus 2 on square root of 3. Okay. So what do we have for part B here? We have a transformation, some matrix. So this is just a dilation matrix, and one of the numbers is 1, which is quite nice. So we're just varying this other dilation here. So this is a dilation from, which axis is it? It's from the x-axis, because we're scaling our y values. So if you scale your y values, it's moving away and sort of closer, depending on what the number is to the x-axis. So we have a transformation. Let's the graph of the function h be the transformation of the line that passes through the points A and P. So it's the line we just found under the transformation t. Okay, so we're going to transform that line, that tangent line somehow, and we're going to get a new graph, or the new function h. Find the values of q for which the graph of h intersects with the unit circle at least once. Okay. So remember, what is q doing? So first of all, q is a dilation from the x-axis. So what does a dilation from the x-axis mean? It means that you're just kind of moving this line up and down almost. It's not a translation, it's you kind of scale it. So first of all, notice that this line's always going to, no matter how you transform it, at least under this transformation here that's prescribed, the point at 2, 0, it's always going to stay fixed there. Because if you're on the x-axis, no matter how much you dilate from the x-axis, you're always going to stay on the x-axis. What's really going to move is the whole entire line. So this line's kind of going to pivot around the points 2, 0. So I guess, what are the possible pivots, if that makes any sense, for which this line intersects the circle at least? Was it at least once? Let the graph of h intersect the circle twice. No, this is at least once. So, for example, if q is equal to 1, then we don't do anything. So we're just going to have this picture over here. Now we could also move this line, for example. Let's choose red. Red. We could also move it down over here, or over here, 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 or here. Those would all intersect the circle at least once. So it could be any dilation in the range negative 1 to 1. Because if you're at negative 1, then you're going to be hitting the tangent at the bottom of the circle here. And if you're anywhere in between, you're going to get a line that's somewhere in this cone here. If you're outside, then you're not going to intersect the circle at all. You're going to be out over here. So these yellow lines are not what we want. These yellow lines is when our Q is greater than 1 or less than -1. We don't want that. We only want the red lines. So Q has to be between -1 and 1. That's our answer. So Q is on the interval -1 to 1. That's what we want. Okay, let the graph of H intersect the circle twice. Find the values of Q for which the coordinates of the point of intersection only have positive values. What is it saying over here? So this is the graph of H, that's still the transformed function. Find the values of Q for which the coordinates of the points of intersection have only positive values. So for example, if we have a line like this, then here are the intersection points, and clearly not all the coordinates have positive values because the x value on the left hand side of here, it's negative. So how much do we have to restrict things? I guess the furthest we can go is over here. Let's use a ruler for this. Let's use a ruler. So we're fixed at 2, 0. The furthest we can go is right over here. Any lower, then we're going to introduce negative coordinates, which is not what we want. I'm assuming that's what the question is asking. So we're finding the values of Q for which the coordinates of the points of intersection only have positive values. Okay. So this is intersect the unit circle twice. So first of all, our upper bound is 1. We can't be greater than 1. And we can't be less than this red line. We can't move it lower. So what's the dilation required to get to the red line from the black line is the question. Okay. So first of all, notice that the y-intercept of the black line is 2 on root 3. So this y-intercept is 2 on root 3. Let's not use black there. So this is 2 on root 3. Now, what's the y-intercept of this point on the red line? Well, it's just going to be 1. So what's the dilation required to get from 2 on root 3? You have to multiply by some dilation, let's say q, to get to 1. What's q going to be? Q is going to be root 3 on 2. So if you apply dilation of root 3 on 2, you're going to move that black line onto the red line. And you don't want to go lower than that. Okay, so there's one possible set of values. So it could go from, so this is only positive values. So I don't think it would include 0. So you would want to exclude root 3 on 2. And you'd also want to exclude 1 because this is intersect the circle twice. If it's on 1, then it's only once, which is not what we want. So this is only one side of it because you also got to remember there's the other side as well, which is, everything reflected over. So the red line on the negative side, so underneath the x-axis. Actually, no, that wouldn't work because if you're underneath, then you'd have negative y value. So that's not negative. That's not positive coordinates anymore. So I guess it's only these set of values here. So Q is on the interval root 3 on 2 to 1 is our answer. Right, we're almost there. Part C, for Q between 0 and 1. So what does it mean for Q to be between 0 and 1? It means that this line can only exist in the upper half plane. So something like this. And if it's 1, then it can't be, it's the tangents, is the maximum. So let G be the function that gives the area of the triangle OAP prime in terms of theta. To find the function G in terms of theta. Okay, so we have our angle theta. The question is, how do we get the area? Well, that's not too tricky to do. You just apply the formula for area of the triangle. So G of theta, that's just going to be 1/2 times base times height. But that's 1/2. What's the base of this triangle going to be? It's always going to be 2 because you're always going to intersect the points 2, 0 there and you start at the origin. So the base is 2. What's the height going to be? Well, you have this angle of they have this angle of theta here. The height is the y value of the point P prime, but that's just given by sine of theta. So this is sine of theta. Determine the maximum possible area of OAP. So G equals sine theta is the function that gives us the area, and we want to maximize theta. So how can we do this over here? So first of all, what's the domain of theta? The domain of theta looks like it's from 0 to somewhere. I think it would be pi on 3, right? So theta would be on the interval 0 to pi on 3. I think if you define the function g, maybe you have to put in the domain as well, so maybe we'll put in 0 less than theta less than pi on 3, just to be safe. So we put that over there. The reason why it's pi on 3 is because q is at most 1. And I just realized because of this domain here, so domain's always important, we can't include 0. So because you can't include 0, this is just going to be a less than inequality here. Because the area can't be 0, which makes sense. So this is just going to be open brackets. What was I saying before? Why is it pi on 3? The reason why it's pi on 3 is because the upper bound is 1 here. It can be at most 1. Now what does q equals 1 look like? It looks like the tangent here. And we calculated before, if we have this tangent line and we consider the perpendicular line that goes through the origin of the circle, that angle, which we have, is exactly pi on 3. So we have this domain here, which is nice. Now we want to find the maximum possible area. So how do you find the maximum possible area? You can first of all find turning points. So you can find g prime, for instance. So what's g prime of theta? It's just going to be cosine of theta. And you solve the derivative equal to 0. So how do you get cosine of theta equal to 0? Well, you could have q is between 0 and 1. Where P prime is always the point of intersection that is closest to A. Okay. So it can only go up to pi on 3, which, okay, that makes sense. So you're going to get theta is equal to pi on 2, but that's outside of the domain. 0 to pi on 3. That's not what we want. So therefore, we have to take a look at g at one of the endpoints. It's a g of 0 or g of pi on 3, because the maximum can only occur at the endpoints. Now g of 0 is going to be 0. G of pi on 3 is going to be not 1/2, root 3 on 2. So because root 3 on 2 is clearly the greater value, we're going to take this as the greatest possible value for the area of OAP prime. And with that, we are done. So we managed just to get under the 1 hour time limit, which is good. So yeah, not too bad of an exam actually. There was some silly questions like the donut question. I didn't like part B at all. And yeah, not too bad of an exam. Arithmetic was a bit interesting though. At least it wasn't as bad as the 2021, but yeah. Hope you guys enjoyed this video and found it helpful. If you have questions, feel free to leave them in the comments, and I'll see everyone next time. Bye bye.